Okay, just a moment. Can you see the slide?
Yes.
Okay. Thank you very much, first of all, of inviting me to this event so that I will present this work that was part of the last activities in my PhD almost 10 years ago, and that were related to SystemC, and the topic is fault injection methodology for the system level reliability analysis of computing systems modeled in SystemC. Actually, what I will present today is a framework and a methodology for the reliability analysis based on fault injection of multi-core systems running parallel or sequential applications modeled in SystemC and TLM. Since I will not be able to attend the entire meeting, if you have any question, please interrupt me during the presentation or at the end of my presentation. Mission and safety critical applications. Here in this slide, I present some example. You see the electronic part of the automotives, of cars, of motor cars, rovers, space systems, and so on and so forth. So, there is the necessity to perform a reliability-aware design of computing system. We need the system when acting in a safety or mission-critical application to be able to deal with faults, in particular transient one, today is the reliability analysis. We have a system, we would like to see how the system behave in presence of, when a fault occurs, and we would like to understand if the system is able to manage the faults. And the common practice in this reliability analysis is fault injection. We intentionally corrupt the execution of the system, of a model of the system, or the prototype of the system, or the final implementation of the system, in order to see if the system is the running application is able to obtain the same result of the golden run, the run without default. Okay, if we analyze the literature, we can see which are the limitations that we found 10 years ago in the common practices for fault injection. First of all, fault injection is mainly performed in the late design stages, especially in the industrial practice. Fault injection is performed at the end, on the final prototype, on the final system. And this is not efficient. Why? Just because if you find any problem, the feedback has to be performed to the first parts of the design flow. That means that we spend a huge amount of time going back, and we spend a lot of monies redesigning the system. What we would like to do is perform a reliability analysis right from the early phases of the design flow, so that if we find any problem, we can immediately fix it. We can immediately perform a reliability-aware design. Second limitation is the fact that mainly fault injection and reliability analysis is performed by analyzing just only the final output of the running application. And this is not good in case of complex systems, complex applications composed of many tasks that interact to each other, because we would like to understand in the case of a fault occur, where the fault occurred, and how the other parts of the system react to the fault, if the other parts are able to absorb and to manage the occurrence of the fault. Finally, Third limitation is, okay, mainly fault injection was performed by analyzing final results. Sometimes also internal memory elements were traced in order to analyze the raw data, the architectural values flowing into the system. But actually, we can see in this slide how these values are not very useful. Just consider here in this slide what I did was to compare for each register of a processor the golden run, the value in the golden run with the value in the faulty run, and here the line demonstrates here that there is a different value in the faulty run starting from here. Okay, and here we see we have different errors. Here we have errors. Then the two values in the golden run and faulty run are the same, so on and so forth. But obviously, we agree on the fact that this graph, this plot, is quite useless. It does not give us any useful information on how to better design, how to harden the system. Okay, so the goal of my talk is to present a new framework and the companion methodology for the system level fault injection based reliability analysis in multicore specified in SystemC and TLM. Why SystemC and TLM? Just because we model the system in the early stages before producing and manufacturing the system. What we do is we build a model. And every one of us here in this meeting agrees on the fact that we would like to use SystemC and TLM to model the system in order to evaluate the characteristics of the system, the performances, the power consumption, and also the reliability before implementing it. And SystemC is the tool that we would like to use. And therefore, what I propose here is to perform a reliability-aware analysis based on fault injection in SystemC. Key points of my analysis are, first of all, key points are to try to overcome the limitations of the literature of the previous approaches, and in particular by supporting an accurate definition of the fault campaign. So with the methodology I'm going to present, we are not selecting randomly for the location of the faults, but we select also the location of the faults, for instance, by considering which is the functionality of the system of the application running on the architecture that we would like to test. Then the second key point is the capability of performing an error modeling at both monitoring, scusate, sorry, error monitoring, sorry, not only at architecture level, as I demonstrated in my previous slide, but also at application level. The methodology I'm going to present is able to abstract the raw data, the raw architectural data at application level, just to understand when a function, for instance, is executed in the application, if it's executing, it has been called with faulty, erroneous parameters or not, wrong parameters or not, due to the occurrence of a fault occurred before the invocation of the function. Finally, what the methodology support is a customizable error analysis and classification approach. The methodology is able to support the analysis of the complex multicore system, not only in the monitoring of the main output and the classification of the effect of the fault in erroneous result, crash, no effect on the final result, but also allows to perform an analysis of the internal propagation of the error at application level, especially in the execution of the functions. Okay? Is there any question? Is it everything clear up to now? Okay. The reference system, which is the system we would like to evaluate? The system we would like to evaluate is as an hardware architecture on the right part of the slide that is a processor-based system composed of one or many processors. Here we have just only one processor for the sake of simplicity. Memory elements, other accelerators, a bus that interconnect the various components, and the hardware platform is modeled by using SystemC and TLM. On top of it, we would like to run an application that can be modeled as a task graph we assume to run, to write, we consider here in this methodology, we implemented the prototype to consider, to analyze C code, C applications, applications that actually can also exploit, are not composed just only of software running on the processor, but they can also invoke hardware accelerators. Here, for instance, we have two tasks. You see here, the first one, the last one, that are in charge of transmission of the data in input and in output, that are actually invoked by the main function here, by the program, by the application, by the software, but are actually executed in hardware. Here, we assume this application model as a task graph to be executed in C, and for the cycle of organization of the code, we split each one of these functions of these tasks, sorry, in a different C function. So we have a C code organized in many functions, here invoked in a sequence, since we have a chain by the main function of the program, of the C program. So this is the system we would like to analyze. Okay, so how to before discussing about the fault injector we implemented and the error analysis methodology, we have to discuss about a bit about the background, and in particular we have to discuss about a simulation platform, a virtual platform that is called RESP, that was developed. It was a research activity jointly performed by Politecnico di Milano and the European Space Agency. And the idea of RESP was a system-level simulation platform for multicores, where the hardware components, the multicores, were modeled by using SystemC and TLM. On top of it, on top of it, we built a Python console, a Python infrastructure in order to manage the hardware components specified in SystemC. So let's assume the idea is the following. We have a repository of SystemC components, and the instantiation and the connection of the various SystemC TLM components is directly performed in a Python console, so in Python. And the interconnection between the C++ word, the SystemC word is C++ actually, and the Python word was enabled by means of specific libraries automatically wrapping C++ components and integrating in the Python console. Why did we use this strategy? Actually, to exploit all the very interesting characteristics of Python that are the scripting capabilities and the introspection. As we know, Python as a console, we script, we don't build a program, write a program, we compile it, and then we execute it. What we do is we actually write lines, and lines are executed on the fly. So we wanted to use this peculiarity also to instantiate the architecture, the SystemC architecture, to interconnect the various components and to execute the simulation. Moreover, Python offers also the introspection. That means the capability of querying the internal status of C++ classes. For instance, to read or to write the attributes of each class, so of each SystemC component. So this was the platform, and these specific peculiarities, the introspection, the scripting capabilities, were particularly exploited also for the fault injection, as we will see in the next few slides. Oh, here, you see here a run of a simulation. We see how this is the Python console. You can see here, we loaded the Python script in which we instantiated that contained the instantiation of components and interconnection of the TLM ports. You see, we actually called the run from the console, the run simulation command, invoking the run function, SystemC function, and the underlying SystemC engine runs and performs the entire execution and the entire simulation. Okay, so based on this this idea, on this platform, what we implemented was a fault injector. A fault injector. Here we see in the middle of the slide, we see the picture of a SystemC TLM model of a multicore. We can see two processors, the bus and an hardware accelerator and memory. And first of all, we used the so-called simulation commands in order to enable the fault injection, the corruption of the internal status of the components. That means that we can simulate the transient faults actually by manipulating, by stopping the simulation, manipulating the internal status of the processor, for instance, and then resuming the simulation. Here we see an example. We loaded the same.
Could you remove? Okay, is that intentional? Because it's kind of hard to see when you have that window floating in front of the slides.
Here, you see here, this one?
Yes, it's in the way of the slide.
Yeah, I know. It was intentional. It was intentional. I would like to comment the screenshot and then I will remove the screenshot. Okay? Okay, so here you see what we can do with the introspection in the scripting console of Python. Just a moment. Sorry, I had to stop Alexa, otherwise he will start speaking together with me. Okay, so here you see we load the architecture, then we start the simulation just only for 500 milliseconds, and then here we implement the fault injection. You see, we read the next program counter, the variable containing the next value of the program counter, and here you see 88 is the next program counter value. Okay? What we can do, we can corrupt it, as you can see, by simply writing the content, by using the introspection, by calling in Python the C++ functions, the methods of the SystemC object representing the processor. And then we restart the simulation. This strategy is called simulation commands. So with the simulation commands, what we can do is to corrupt the internal status of the component. But to remember that here we have functional models. And in particular, models that we have in general with TLM are, for instance, implements the instruction set architecture of the processor. That means that it contains a reduced number of elements representing the overall registers of the final implementation of the processor. We may inject, for instance, in the program counter, we may inject in the instruction register, we may inject in the register file because they are specified in the instruction set architecture. We cannot inject in all the registers of the pipeline just because those registers are not specified in the instruction set architecture, but they are implemented in the final RTL architecture. That means that in order to simulate faults at this level, we have to perform to model the single bit flip in RTL register as a more advanced corruption. We have to analyze at RTL level the effects of the fault on the register we have in the instruction set architecture, and then therefore we have to model the fault as a multiple corruptions of different registers that are exposed in the instruction set architecture. In the same way, in order to model false in registers not available in the functional specification, the second strategy is to corrupt the transmitted data. Okay? For instance, to represent false in the registers involved in the transmission, in the mechanisms in the hardware implementing the transmission on the bus and between the processor and the hardware. What we can do is to inject the fault here. And here we can inject the fault by using a special TLM component that we can automatically, that the simulator automatically integrate, that is called a saboteur. The saboteur here you see is actually a standard. Here I report also a sketch of the code. Receives the transaction from the master, corrupt the value, and then transmit. You see here the 4 becomes a 5 and transmit the value to the memory. And this is the second injection strategy that we implemented into the simulator. Same facilities used for the fault injection, REST facilities used for the fault injection were also used for implementing monitoring facilities. And in particular, processor models implemented in RESP that are implemented mainly by using a processor model generator exposes a kind of debugging interface. The debugging interface can be used in order to monitor all the instructions that are executed on the processor in order to understand if the processed values are corrupted or not, are wrong or not. Okay? And in particular, we performed this kind of analysis at function level. That means that here, the debugging interface is used mainly to capture when a function is called or is returned in order to analyze the transmitted parameters. We implemented some tools within RESP by exploiting the application binary interface of the processors involved in our models in order to interpret the raw data, the content of the registers, in terms of parameters exchanged with the function. Just to understand if each function that represents the task I presented in my previous slide has been called with erroneous parameters or with correct parameters. Okay? Finally, we also implemented, in order to monitor the system, the possibility to enable the possibility to inject probes on the TLM ports. Probes that are more or less have more or less the same structure of the saboteurs. And the idea is to integrate here a probe between the two TLM ports, the master and the slave port, in order to receive the transaction, analyze the content to see if it's the correct one or the expected one, and then transmit it to the memory. And back also on the way back. And finally, the simulator also enabled the possibility to register specific custom Python functions that are called by the SystemC scheduler every delta cycle. So that at each delta cycle, we can call the Python function that, thanks to the introspection, the introspection is able to read the current status of the various components and trace information, log the internal status, or based on custom analysis function, decide if the execution is going in a good way or not. Okay?
Hello, Antonio.
Yeah.
I have 3 questions for you.
Yeah.
The first one, so I understand that you need to modify the scheduler, the kernel of the SystemC, I mean, for adding these Python capabilities.
Okay. I was not the author of the RESP. RESP was implemented by a colleague of mine, just also to to answer to a question I read in the chat. RESP was open source. Unfortunately, we are discussing about a work we did more than 10 years ago. RESP was presented at ASPIDAC in 2009. Actually, it is discontinued because all the colleagues that worked on that simulator left Politecnico and moved for another job. So actually, also regarding to this presentation, let's say today I would like to present the lesson we learned by this experience, but you cannot reuse the code as it is. Okay, it's a kind of lesson learned. I present what we did and what we learned at that time, but the code is not available anymore. Okay.
Okay, thank you.
Regarding to the calling of Python every delta cycle is expensive, obviously, and obviously we don't want to do it every time. We do it just only when we need to do it. Okay, Jacob. So it's a matter of trade-off, as usual. As usual, when we perform fault injection error analysis, we have to trade off. Obviously, the more the analysis we would like to do, the more the effort, the execution time, the expensiveness of on the execution time. It is obvious. So it is a matter of trade-off. Also, another example, as usual, tracing and logging all the internal status of the system eventually will generate a huge amount of data that maybe are not useful. Okay? So it's a matter of trade-off, a matter of what we need and what we would like, to do and to analyze. Okay.
So one more question. It's so if you have the introspection injection strategy, why do we need a saboteur?
Okay. I was not able to explain this point earlier. Actually, is a problem of fault modeling, and I try to explain. Okay, we are focusing on transient faults. Okay, so the transient fault is a fault that corrupt a register. We model the SU, the single event upset, on the register transfer level specification. Do you agree with me, Ernesto?
Yes. Yes.
Great. The problem here is that we don't have an RTL model of the processor, but a functional model based on the instruction set architecture. And in the instruction set architecture, a subset of the RTL registers are specified. Okay? Ernesto?
Yes.
Okay, great. So in a functional model, in a functional ISA-based model, we have to model faults as the effect of the resulting errors on what we can see and what we can corrupt. So what we can corrupt, what we can see, what we can read is the subset of the registers and the interfaces. Okay? So just to give an example, here on the RTL model, we will have registers for sure on the port. Do you agree, Ernesto?
Yes.
But in the ISA-based model, we don't have registers. So in order to model the effect of faults actually corrupting the registers connected on the last part of the processor connected to the interface, okay, what we have to do is to model those faults as errors in the transmitted data. So for this reason, we use the saboteur.
Okay, so that means that the first strategy cannot alter the TLM.
The first strategy is able to inject just only a subset of the faults that actually may corrupt the final implementation of the processor. Okay?
And which are these subset? Yes,
the subset is based on, you can inject just only in the registers that are exposed by the instruction set architecture.
Okay. Okay, I get it.
Okay.
Thanks.
Sorry to be that guy, but time is running. So
Okay, yeah, I have to speed up.
Yeah.
Okay, so this was the architecture, the framework, and based on that, we implemented a system level reliability analysis methodology. How much time do I have?
actually zero.
Zero?
Yeah, our
Ah,
time is really up. But if you have short wrapping up words you want to
okay,
say.
okay. I will conclude in 5 minutes. So, based on this fault injection, this framework, we implemented a methodology to try to analyze the faults, the effect of the faults at application level. And this is the picture, okay, of the overall methodology. So, just to give some details, first of all, what we did was a static analysis of the application in order to build, to analyze and to build the task graph I presented you in my previous slide. That means we cross-compiled the application and we disassembled it in order to have the list of the functions. You see here the list of all the functions, and here you recognize the same function we had in my previous slide because this is exactly the same example. The memory addresses of the instructions here, and based on the application binary interface, here you see we have the list of all the parameters and where they are mapped in the registers. Why do we need this information? Just because when we run the fault injection simulation and we would like to analyze the effect of an injected fault at function level, what we do is we use the debugging interface of the processor in order to intercept when, for instance, the edge detector is executed, and when the edge detector is executed, we can go to access, to read, to monitor the content of the various registers. And here, based on this information, we know that the register 0 contains the pointer of the input image, register 1 contains the pointer of the second image, and the other two ones contains, you see, the width and the height of the image. So we can abstract raw architecture level information to application level in order to analyze, to be able to monitor and to analyze the execution at application level. Now, raw architecture data are transformed in meaningful application level informations. So, based on that, we also performed, during the preliminary analysis, we performed also a static architecture, not only of the application, but also of the architecture. That means we extracted all the injection sites, okay, where we can inject faults. That means all the attributes of the SystemC component representing registers. And then finally, what we do is to try to perform a golden run in order to characterize the execution, the behavior of the system in absence of faults. And in particular, what we do is we collect relevant traces to understand which are the nominal golden results, and we build the so-called execution flow graph. You see here, what we did was to build a graph with all the events related to the entering in the function, the exiting of the function, and based on the interface, the debug-like interface I discussed and the information we extracted during the static analysis, we are able to collect information that are, for instance, at which instant of time the function is called, for instance, on which processor is executed, and moreover, which are the values that are saved in each parameter used by the function. So again, we are abstracting, we are interpreting architecture raw data at application level, and this interpretation gives a meaningful information to those data. Okay, so here we know how to analyze at application level the execution when we will inject the fault. Moreover, also the injection defaults we can perform thanks to this.
Antonio, I think we really need to wrap up.
Okay. So I will not explain the various details of the methodology. Okay, based on that, just to conclude, the idea was to add to the debug-like interface and to the probes I discussed so far, a configurable monitoring and classification module capable at monitoring and analyzing the status of the system during the simulation. And the classification is performed with a custom approach that is tailored to the application. And okay, finally, there is no time to present the case study that was devoted to analyze the reliability of a TMR'd edge detection detector running on a multicore system. In any case, if you are interested in the second part of this presentation, please, you can read the first paper here, a fault injection methodology for the system-level dependability analysis of multiprocessor embedded systems. Sorry if I missed the deadline. I tried to answer all the questions you asked. Okay.
Yeah, thanks a lot, Antonio, and thanks a lot to the people engaging in the discussion. Antonio, could you please send the slides
of course, yes,
to me afterwards or to Christian,
yeah.
and we will collect them and put them on the site. So
okay.
Thanks everyone. Thanks to you, Antonio, especially. You will get you are now receiving a virtual applause. So thanks for your presentation, and let's move on to the next speaker.
Thank you.